Welcome to this lecture. Basically, today's lecture is a continuation of our previous lecture, where we have started discussing properties of multiple random variables, and in that we started discussing some of them, and today we will be continuing of the rest of the properties. So, if you see that in the last class we discussed about their moments, and these all we are discussing in the context of the multiple random variable, and these things we discussed earlier also with respect to the single random variable, and you know that they are same concept we are using here when we are discussing those basic properties. Say for example, when we discuss the moments also, we have seen in the last class that how the concept is taken forward from the single to the bivariate case, and from the bivariate to the more than two random variable cases. So, now when we are discussing about the multiple random variable, that time we have to there are some more properties may come which may not come in the with respect to the single random variable. For example, that the conditional distribution we discussed earlier. Now, these conditional distributions are in respect to the multiple random variables only. Minimum we need two random variables, where we can say that the distribution of one random variable when it is conditioned on the outcome of the other one. So, those are the conditional distribution that we discussed. Now, related to those things, there are some properties also we can we will come in this multiple random variable case, and we will be starting our today's lecture in discussing of those theories and some related problems in civil engineering. So, at a glance, if we see what are the things that we discussed in the last class, we discussed the moments, we discussed the covariance, we discussed correlation coefficient. Now, today's class we will start with one example problem which to cover this covariance and correlation coefficient, and after that we will discuss the conditional mean and conditional variance, and gradually we will also go the moment generating function. If this one, if not today's class, then maybe next class we will continue the moment generating function, but if time permits we will cover this one also. So, one thing what we are what I am trying to say here is that this conditional mean and conditional variance, when we are talking about these things was not there in the single random variable, but these things basically we are taking the theory from the conditional distribution. The conditional distribution in case of multiple random variable was discussed earlier. Now, we will just see some of the properties when the distribution is conditioned on the other random variable. So, in the last class where we stopped is that after discussing the theory of this covariance and correlation coefficient that we have seen, and this is a basically if you recall that correlation coefficient is a standardized measure with respect to that covariance. Now, this correlation coefficient can vary from -1 to +1, that also we have seen. So, today's class we will start with one example problem where we will see that covariance and then correlation coefficient. Basically, if you recall in the last class we have taken some special problem where we have taken the problems with the independent random variable, and I just gave one indication at the end that we got the covariance equals to 0. So, there could be two reasons. One reason is obviously whether the random variable are independent or not, and other reason that they do not covary with each other, that is why it is 0. So, means if the random variables are independent, then obviously the covariance will come 0, and we have seen one such problem in the last class where the covariance is 0. And so, if you check that whether the marginals, the product of the marginals are equal to their joint distribution, which is the proof for the independence between the random variables. So, that that was the point that I indicated in the last class. And the other problem also, the way we have taken, we have started with the assumption of that independence, and finally we have seen that covariance is coming to be 0. Now in this class that we are starting with a more general problem where the covariance need not be 0 always, and from the covariance using whatever the theory we have discussed in the last class, we will also calculate what is the correlation coefficient. Now this correlation coefficient and the covariance that we are getting, we are starting from their distributional properties, the joint distributional properties. So these are based on the whatever the distribution it is, but in the practical application many times we generally have the data, and based on the data how we can get the estimate of the correlation coefficient. Those are basically called the sample estimates, because we have the sample and from the sample we are estimating these measures, and that is the statistical part, and we will take up these issues in module 7. Here what we are discussing is these measures with respect to the population, means the entire population of the random variable. So that means basically we are starting from their joint distribution. So the problem states in this, there are two projects, and there is one project, and in that project there are two components, and two components can take different times, and basically in any project, including the civil engineering projects, there are many interrelated components are there to successfully execute those projects. Now here we have taken two components for the simplicity sake. There could be more than two components in a project, and here what we have taken that their time taken, there is a duration of each project, that is x and y. So the duration in years of two components of a project A and B are denoted as x and y. So this the duration in years which is denoted as x, that is the component A takes x and component B takes y. Now the component A cannot be completed before the completion of component B. So as I told that components are always interrelated, so it requires to be complete the one component first, until and unless you finish this one you cannot go for the second one. So like that. So here as the component A takes the time x and B takes time y, so that means that x should be greater than y, and the total duration of the project is 2 years. The joint density is given by, or it is assumed like this, that f x y is a 3 by 8 x, where this y is y ranging from this 0 to x, and x range from this y to 2. So that total it is below less than 2 years, and the y is less than x, and otherwise it is 0. Now when we declare that this is a joint distribution between x and y, then obviously the total in a single random variable we call the total area below the curve, but here when we are taking the two random variables, you know that this is the volume now, because it is in 3 dimensional now. So the total volume below this surface should be equals to 1. So that you can check yourself whether this is a valid PDF or not first. So what in this problem we are looking that we have to determine the covariance between the duration of two components, that is between x and y, and their correlation coefficient between these two random variables x and y. Now if you recall the theory that we discussed, that covariance, if we want to calculate, it should be the expression of x y minus expression of x multiplied by expression of y. So first of all we have to calculate the expectation or expected value of x y, x and y. Now the expectation of x y is you know this formula we discussed earlier. So x y multiplied by their joint density, and we have to integrate over the entire range. Now when we are integrating over the entire range, there is you know this integration over that area that you have to take the limit. So first we are taking the integration with respect to x, so it is y to 2, then this f x y is that 3 by 8 x and x y multiplied by, and then y equals to 0 to 2. So the pictorially if you want to see this one, that is here on the pad, if you see that fx y is equals to 3 by 8 x for the range that is 0 less than equals to y less than equals to x less than equals to 2 was given here. So, if you want to see this one here, so basically if this is your x and if this is your y, then basically you are getting a area like this where it is say 2. So, the PDF is defined over this area where x is greater than y. So, over this area it is defined. Now, when you are taking this range for this entire support of this random variables, then you have to either consider a strip like this or a strip like this. So, so if we here the way the limits are taken, if you take a strip like this, that means your that range of x. So, here you know that x is equals to y in this point, and here that your x is equals to 2. Now, this strip has to be moved from the this to this in the y direction, direction. So, here the y is equals to 0 and here the y equals to 2. That is why when you are doing this integration over this area, that means you are taking that this one, this x. So, that x y, then f x y, that means 3 by 8 x. Now, when you are taking that integration limit x, so that means you are taking this. So, y is y from y, that is x equals to y to 2, and then when you are taking with respect to y, you are taking 0 to 2. So, this is the way how these integration limits are coming in. So, that is what is shown here. So, this integration from y to 2 and 0 to 2 over this range to cover this entire range of this support of both the random variables. So, if you do this integration, now you will get that expectation of x y is equals to 6 by 5. So, just we have to follow these few steps, and then if we want to know what is the expectation of x, then this is easy, because this x multiplied by this range. So, expectation of x means we have to integrate out the entire y, and 0 to x should be the limit for the other one for this. So, this should be multiplied by this x and take that entire range again, and if we do this one, then we will get that expectation of x is equals to 3 by 2. So, here if you just see, this is also means taken the over the entire range, but here the way the integration is defined is in a perpendicular direction. So, first we are taking that y limit. So, that is why this limit is 0 to x, and then we are taking the x. So, that is why it is 0 to 2. So, that means what I am taking is that this also can be done if you see in this writing pad, then either of this, or you can take this one also. So, that means you are taking that integration with respect to y first. So, y equals to 0 or to y is equals to x here, and this one you are doing it from the for the entire range of this x. So, where the x equals to 0 here and x equals to 2 here. So, in this way also you can do, and this is exactly is shown here for this limit here, where that y for y it is 0 to x, and for x it is 0 to 2. So, if you do this one, then you will get the expected value of the x is equals to 3 by 2. Similarly, the expected value of y also you can take, and if you take this one, then you will get the with the suitable limits, and after doing this integration, we will get the expected value of y is equals to 3 by 4. So, we got expectation of x y, we got expectation of x and y. So, if we just fit in this covariance formula, the covariance between x and y is equals to expectation of x y minus expectation of x minus expectation of y, which is 6 by 5 minus 3 by 2 multiplied by 3 by 4, which is coming to be 3 by 40. So, the covariance here we have seen that it is they covary with each other, and their covariance is non-zero, and which is 3 by 40. Now, the second thing that was asked in the question is that we have to calculate the correlation coefficient. Now, to get the correlation coefficient, you know, we have to find out that their individual variance, means the variance of x and variance of y, and that we have to take the square root, and with that quantity we have to standardize this covariance, then we will get that correlation coefficient. So, the formula is this, that correlation coefficient equals to the covariance between x and y divided by the square root of the variance of x and variance of y. And now, to calculate the variance of x, this was discussed earlier. So, this x, this is the variance, you know, it is the central moment with respect to the mean of that random variable, and that we have, this is the second moment. So, that is why we are taking the square, that multiplied by their joint density and taking this integration with the over the entire range of this x and y, as it is the bivariate case. So, we will get what is the variance of x. Similarly, we will get the variance of y if we take this, if we follow this in integration. So, we have to solve these two first, along with the covariance we know the what is covariance. So, we have to solve these two to get what is their quantity, and then we can fit it in this equation to get their correlation coefficient. So, this sigma x square, when we are taking, we are taking this one, and the mu x we have already determined, that is the expectation of x, which is 3 by 2, we have seen it earlier. Now, we are placing this one, and with the suitable limits for the entire range of this support of random variable. And if we do this integration step, we see that the sigma x square is coming to be 3 by 20. And so, sigma x square is 3 by 20, and similarly, if we get that sigma y square, where we are taking the y minus mu y, and this mu y, you know, this is the expectation of y, and this expectation of y is equals to 3 by 3 by 4. And if we take this 3 by 4 and with the suitable limit of this entire range of the random variable, then what we will get? We will get the sigma y square is equals to 19 by 80. So, this is the sigma y square. Now, if we put these two in this equation of this correlation coefficient, then we get that. So, this will be the entire square root, because this root should be go up to here. So, 3 by 20 multiplied by 19 by 80, take the whole square root of this one, then in the numerator it is 3 by 40. If we do this one, we will get the correlation coefficient between x and y is equals to 0.3974. So, so here we have seen that one problem we have taken, and in that problem we have seen that there is some covariance, and from that covariance we calculate the correlation coefficient as well. Next, we will move to the conditional mean and conditional variance, and you know that these were not discussed with respect to the single random variable. This is discussed only with the respect of the multiple random variable and the minimum 2 random variable we need. And basically, we will start our discussion with the 2 random variables only, and we will see that what is this conditional mean and conditional variances, which is our next discussion. So, here if we see that this conditional mean and conditional variance, that means that these measures are determined from the conditional distribution discussed earlier. So, conditional distribution, we have seen that from the joint distribution. Now, if the outcome of the the range or the outcome of the one random variable is known, now what should be the distribution of the other random variable? That was the theme of this conditional distribution, and that theory we have discussed earlier. Now, from that conditional distribution, so once we have decided that this is the conditional distribution, then that distribution function also follows the basic axioms of this PDF, that so it should be greater than, this will be a non-negative number greater than or equal to 0, and the total probability, if we integrate it over the entire range, then it should be equals to 1. So that too should be followed. Now simply means if we just extend the concept, then so that we should treat as a distribution function, and from that distribution function we can calculate whatever the statistics or whatever the measures we want to calculate. So similarly, the conditional mean, when we are referring to, that means from the conditional distribution we can calculate following the equation of this, how to calculate the mean. Following that equation we can calculate the mean. So, and that mean will be called as the conditional mean, because that distribution is already conditioned on the outcome of the other random variable. So in case of two random variables, because we are always starting with these two random variables first. So in case of two random variables, the mean or the variance, or I should say that this is of any moment of any order, because mean you know that is the first moment with respect to the origin, variance is the second moment with respect to the mean. So basically when we are talking about these measures with respect to these measures with respect to the conditional distribution, basically there is no need that we have to stop only in this mean and variance. It can be go on for the higher moments as well. But anyway, to start with the discussion, we are taking this mean and variance, and that too for the two random variables. So this mean or the variance of one variable depend on the condition imposed on the other variable. So now if we recall that our discussion on this joint distribution, and from the joint distribution to the conditional distribution, that means we are considering the distribution for a particular value of the other random variable, and that we have seen that how to normalize that one to make sure that this total in case of the single random variable or the two random variables, then the conditional is for conditional distribution is the single random variable. Now how to make that one standardized to make it the total area below that random variable equals to 1, that we have seen. Now for that distribution we are calculating these measures. So that is why the condition, so the whatever the condition that you have imposed on the other variable, depending on that mean of that original random variable, say x, can change. So that's thus these measures are known as the conditional. So that is why the word the conditional comes before that measure, that is conditional mean or conditional variance. Now if we take up the two different cases, that is one is that discrete case, another one is the continuous case. If we take up these two cases separately, then in when we just discussed that these are the discrete random variables, so two random variables x and y are discrete, and their joint PMF is that your Pxy xy. So this is, if this is their joint PMF, then the conditional mean of x given y equals to a specific value. Now that y equals to a specific value, when we are telling, that means that x on condition y. Now this mean is the expectation of this quantity, that is x given y is equals to y, which is a specific value of the y. Now this one we already know that what is their distribution function from the discussion of the conditional distribution. Now the this conditional distribution, when we are taking, so you know that this conditional distribution, this conditional PMF, that is x given y, this we have seen earlier how to obtain this this particular distributional form. Now as I am trying to say that this is a PMF or probability mass function for the x, and which should follow all the properties that a PMF should follow. So this we can treat as an PMF, and from that PMF, if we want to calculate the mean, you know that this is a standard formula that we have to multiply with that which expectation that we are talking about, so expectation of the x. So that variable we have to multiply, and we have to sum this one for the all possible values of x. Now, if we do this one, then we will get the mean, and that mean is for the condition, and the condition is that y equals to y. So, this is the conditional mean in case of the joint PMF, and this is for the x. And similarly, if we just reverse it for the y, then it will be like this, that expression of y on condition x is equals to x, that is given x should be. So, in this case we have to multiply it with y, and this y, and this PMF should be the conditional PMF of y given x, and this we should get for the so these two are for the discrete case, because we means as these random variables are discrete. So, we are taking this summation of all feasible values of x or y, what the case may be. Now, if so one special case we always discuss, that if they are statistically independent. So, this independence has been discussed in the previous lecture. So, two random variables, when we say that they are independent, so that conditional distribution, that is the probability of x given y or y given x, should be equals to the distribution of x only, because they are independent, they are statistically independent. So, in such cases the conditional mean and variance will be the equal to their own mean. So, so that is what is explained here, that is if x and y are statistically independent, that is the probability of x. So, this should be the probability of x given y, not x comma y. This should be probability of x given y should be equals to its that probability of x, the distribution of the x. So, we know this one. So, this x given y, if we just replace with respect to that px in the previous equation, this is what we have seen. So, that x probability of x given y. So, this we are replacing with respect to the px of x, because these are statistically independent. Now, this x multiplied by px of x for all feasible x, this is nothing but the expression of x. So, that is why it is written that mu x, that is the expectation of x given y equals to this is equals to the expression of x only. This is quite obvious, because they are independent, that x and y are independent. So, that whether what condition is imposed for the other random variables should not influence the properties of this random variable. What is discussed here is that x. So, that whatever the condition is given for the y should not be it should not have any influence on the other one, that is x. So, this should be equals to x. Similarly, that we can write with respect to the y also, that is expression of y given x should be equals to expression of y alone. So, these are the two cases when they are statistically independent. Now, we will just see another case where we will just find out that to get there how the expectation we can just we can see in the other context. So, this starts like this, means that we know that this equation, that is the expectation of x is equals to, these are all we are discussing in case of the discrete random variable, that is why we are taking the summation. So, the expectation of x is equals to their x multiplied by its the density, that probability mass function to get its expectation. Now, this px(x), what we can write is that is equals to, if we just take, so this is basically the marginal of the x. So, how we will get the marginal? The marginal, if we just sum up, if the other variable, that is yi, that is y, if we marginal out this y, then what we will get is that marginal distribution of the x. So, this also we have discussed earlier when we are discussing the marginal distribution. So, this px can be replaced with this equation where we are introducing the joint distribution. Now, so this expression of x is this one that we have shown, and this one is now replaced with their joint distribution for when we are taking it the summation with respect to the all y. Now, this joint distribution also can be replaced with respect to their conditional. Now, how is it done is that this is, so this pxy from the conditional distribution discussion in the earlier lecture we covered that this one is equals to that probability of x given y multiplied by the marginal of y. Okay. Now, if we just if we take now this this quantity, that conditional distribution, multiplied with the x, now this can be replaced with the expectation of x given y, because this we have seen earlier where it is shown it here. So this is the expectation, this is the conditional expectation, which is this expression. So what exactly this one we are using here to replace this quantity. So this one can be replaced with this expectation of this. So basically this one in the sense that including this summation of all x. So what we can write, that expectation of x is equals to the the conditional expectation multiplied with the marginal of the y when we are taking the summation for all possible y. So this one, so before I go to this continuous case, so this is basically what you can say, that it is the expectation of the conditional expectations. So this is the expectation multiplied by their marginal, which is if we take it for this all over this this summation, then we are getting the expectation of the other random variable, which is x. That will also be discussed in the light of the continuous random variable also. Now we will again start the same thing in case of the continuous random variable. Now here, if the x and y are the continuous random variable and their joint PMF is that probability of x and y, that this is the joint distribution is not that x, this is a mistake, this will be comma, that is x comma y, that is x comma y. The conditional mean of the x given y equals to y becomes that mu x on condition y equals to this y, which is equals to, you know, that we have to multiply with the x for this conditional distribution, and over the entire range, if we do the integration, then we will get that their conditional mean. Similarly, we also know, actually we are taking this discussion with the same line that we have discussed just now with respect to the discrete random variable. So we are also taking the same line just to conclude whatever we have concluded in case of the discrete random variable in the light of the continuous random variable also. So that the marginal distribution for the continuous case, that is f x x, is equals to, if we take that if the y is marginal out, that means if we integrate over the entire support with respect to the y, then we will get the marginal distribution. Now with this one, if we just take this mu x equals to this one, and this f x we can just again replace with the joint density, and this joint density is integrated with respect to the y, so that we will get this marginal one. So this f x is replaced with the integration f x y dy for the entire range. Okay. So again this joint one can also be replaced with respect to their conditional distribution, and this conditional distribution is x given y multiplied by their marginal distribution. So this we will get what is that Ex. Now if we substitute this one with respect to, substitute this one means along with their integration with respect to Ax, if we integrate this one with respect to that conditional mean, which is the mu x given y, so then we will get that mu x is equals to mu x given that is conditional mean multiplied by their marginal density over the entire range of the random variable for which the marginal density is taken, to get the expectation of the other random variable. So this is exactly what we discussed in case of this discrete random variable, and here we are putting the same thing in the light of the continuous random variable. Now the expectation of the conditional mean. Now what happens that these measures, when we are taking with respect to the population, then this conditional mean, this itself is a is one random variable. So as this conditional mean or the whatever the conditional measure that we are taking, those are also the can be considered as a random variable. Now as these are also the random variable, this will be more clear when we will be discussing about the sample statistics, because those are also the sample statistics when we are discussing those are also is considered to be a random variable. Here also what we are telling that the conditional mean or conditional variance or this kind of measure, these are also the random variable. So as these are random variable, we can take their the whatever we can whatever the properties we have inspected for a normal for a general random variable, we can also do that one. So here we are taking the expectation of the conditional mean. So this expectation of the conditional mean is the expectation of that random variable. So how it comes, that we will see now. So what we are taking, that this is the conditional mean, that is x given y. Now what we are doing, that we are taking the expectation of this full quantity which is written here e. Now this subscript y, why this is written here is that, now this subscript y indicates that this one, the whatever the inside quantity is the conditional mean, and the condition in condition with respect to the y. Okay, so that's why this y subscript is given, just to differentiate between the there is the expectation of the conditional mean. Now this what we can write again, that this one multiplied by their density, that is the density of this with respect to the y. So this p y you can write. So these are the following the same formula, that is we are using this whatever the random variable multiplied by their distribution and sum over for the all possible values of the random variable. So this one again, now this one we can write that x multiplied by probability of x on condition y, x on condition y multiplied by this p y y, and this one again. So when we are writing that this multiplied by this one, this can be written as the marginal of that x. So that px of x. Now this x, px of x, we know that this is equals to the expectation of x. So that is why the expectation of the conditional mean is the expectation of the random variable. So the expectation of the conditional, so this is the conditional mean for the x. Now if I take the expectation of this quantity, then this is nothing but the expectation of x alone. Conceptually, if you want to understand this one, what does this mean? Suppose that we have considered that say let us refer to this figure. Suppose that there are two random variables. This figure I drawn earlier also. So what we are, so suppose that there is a surface kind of thing, so which can be considered as a joint distribution between the two random variables. This is the x and this is y. Now when we are talking about the conditional, that this conditional means, suppose that this is what is the distribution of the x condition on certain value of y. So suppose that this is the value of the y that we are talking about, and so we are just taking a section through this, and whatever the cross section that we can see here. So this is the distribution when we are normalizing with this marginal distribution of this y, we are getting that value. So for this one we are calculating one mean, and that mean is nothing but the conditional mean. Now so this can vary over the entire range of this y. So this basically, this surface can take any value. Now when we are taking the expectation of those conditional means, basically we are searching over the entire range of this y. Now when we are taking that expectation for the conditional mean over the entire range, which is nothing but the what is the overall expectation of this x. So that overall expectation of this x is nothing but the x. So this is the explanation background with respect to the two random variable, of course. So is that to behind the statement that the expectation of the conditional mean is the expectation of that random variable itself, that is this expectation is equals to expectation of x. Now we will take that conditional variance. Now again following the same formulae for the variance, here also we are taking the conditional variance. That means the variance of x given y. So, variance of x given y equals to small y, that is the specific value of y, is equals to the expectation of x minus that conditional mean. So, this is, if we are considering this is as the random variable, that means we are taking that conditional mean, that square, obviously this is condition on this y. So, this expectation is the conditional mean. So, remember that when we are taking these conditional measures, both this mean and variance, we are taking for that random variable which is condition on the other one. So, if you want to see it here again in this figure, suppose that for this is the conditional distribution. Now, this distribution is having one mean which is not necessarily to be equal to the expectation of x. Now, when we are calculating the variance of this one for this condition, that is y equals, that y is equals to y in this location. So, that means we are considering what is the mean for this condition, which is denoted as, say that mu x on condition y equals to small y. So, with respect to this one, we are taking the second moment to get the conditional variance. This is what is explained in this equation. Now, again there will be similarly two cases. One is that if the random variables are discrete, then the variance will be the summation for all possible x, where the x minus mu x square multiplied by their density, and their density again is the conditional density, that is probability of x given y. If we do this one, we will get the conditional variance for a discrete random variable, for the discrete random variables x and y. Similarly, for the continuous case also, that if the random variables are continuous, then the variance will be equal to from the minus infinity to the plus infinity x minus mu x given y, again this is the conditional mean, square multiplied by their conditional density, and it is integrated over the entire range for that conditional random variable, for that x. So, if we take this one, we will get the conditional variance in case of the continuous random variable. Now, so conditional variance, when we are talking about, now here what we are trying to say, that its relationship with the total variance. So, the total variance we have not used it earlier, but here what we are referring to this total, but this is known in the sense what we are telling, that this, when we are talking the total variance, we are basically talking with respect to the conditional variance. So, conditional variance means for a specific value of the y. Now, when it is not conditioned on any specific value of the y, that means the overall variance that we are considering. So, that we are referring, that we are terming as that total variance. So, total variance, in other word, we can also say that unconditional variance. So, that variance of x. So, just why the total word is used is that just to make it contrast with respect to the conditional variance. We can also call it as the unconditional variance of a random variable. So, this total variance, that is why it is stated that total variance can also be called as the unconditional variance in contrast with the conditional variance, and it can be expressed as this. So, this variance of x is equals to x minus mu on condition of y whole square, and this can also be expressed, that expectation of y on condition that, now this is what we are taking, that the conditional expectation. Now, from this expression, the earlier that we have discussed, so from there the conditional the conditional expectation is the expected value x minus mu x on condition y square given y. Now, if we just expand this right hand side of this expression, where it can be expanded as this one, that is this square. If we just expand inside this square term, there is one mu x is added and other one is just subtracted. So, basically keeping this full quantity same, and then we will take this square. So, taking this one as the first term and this is as the second term, we will just expand it using the simple equation of this square quadratic equation. So, after expanding, what we are getting is that this square is again the condition on y, then that x minus twice of the expectation of that x minus mu x and mu x minus mu y of y, and then mu conditional mean minus this mu x square condition on the y. Now, if you see that this is basically what this x minus mu x is the first moment with respect to the mean. So, you know that first moment with respect to the mean is 0. So, this second term is 0, and the first one that this expectation of x on condition y, that is if you take the expectation of the conditional mean that we have just now discussed, the expectation of the conditional mean is equals to the mean of the random variable itself. So, which is your mu x. So, thus these two equation if we just put there, then what we get is that the variance of the x, which is that expectation of y, variance of x given y plus variance y. So, again here the y when we are talking it is the condition and condition on the y of the expectation of x given y. So, there is a kind of symmetrical nature you can see the when we are taking that expectation of the variance first, and expectation is taken on condition of the y, and then we are taking the variance of the expectation, the variance is taken with respect to the y. So, hence it is stated that the total variance, again the total variance that we are talking about, there is a variance of x of that is the unconditional variance. The total variance is the sum of the mean value of the conditional variance. This is the mean value of the conditional variance and the variance of the conditional mean. So, the variance of the conditional mean, this is what is explained here. What we have referred here, so this is the variance of x, this is might be this is a mistake. So, this will be the x minus mu x whole square. So, there is no condition will not come here. So, now we will take up one problem on this conditional mean, and basically to start with we are starting with the discrete random variable where we can see the all the quantities of this PMF, and we can understand that how the conditional mean is calculated, and we are taking that our same problem that we have discussed earlier for the discrete case. And in this case earlier we have calculated maybe different thing that marginal distribution, conditional distribution and all, and here we will see how to calculate and what is the conditional measure. There is a conditional mean and conditional variance with respect to the same problem. So, that problem is that the stream flow at two gauging stations on two nearby tributaries are categorized into 4 different states, that is the 1, 2, 3 and 4, and these categories are represented by two random variables, one is that x and other one is the y. So, for two different tributaries, two random variables for their category of the stream flow. Now, this PMF of this, so the joint PMF of the stream flow categories x and y are shown in the table on the next slide. Calculate the conditional mean of x at y equals to 1. So, means that the conditional mean of the x given that y equals to 1. So, we have to calculate first what is the conditional distribution. From the conditional distribution we have to calculate their mean as the equation we have just now seen. So, this is their that joint distribution where this x equals to 1, 2, 3, 4, 4 different states and y equals to 1, 2, 3, 4, 4 different states, and these are their marginal distributions. For this is for the marginal distribution of x, which is the summation of each column, and this is the marginal distribution of y, which is the summation of each column. Sorry, this is the summation of each row, and this is the summation of each column. So, this we know earlier, this we have discussed in the earlier problems also. Now, what this problem we are taking is that what is the conditional mean of x given y is equals to 1. So, first of all we have to calculate the their conditional probability. So, joint probability at 1, so that is given y equals to 1, this is these values we can get it from that joint PMF, that is y equals to 1, no, there is a mistake, this should be y equals to 2, so that at 2, so basically we are just taking this column out from here. So, the problem also the mistakes should be corrected as the calculate the conditional mean of x at y equals to 2, not 1. So, this we are taking, and we are just that how to get the conditional probability, that also we have discussed earlier, that is this distribution should be divided by their marginal distribution at that value of y, that is y is equals to 2 here. So, that is the marginal distribution which we can also see in this table, that is 0.446. So, if we just divide, we can get their conditional distribution as that x equals to 1, it is 0.1345, x equals to 2, 0.8072, x equals to 3, 0.0561, and x equals to 4.0022. So, this is the conditional probability. Now, if we want to know their conditional mean, that means we have to multiply with their outcome, respective outcome, and we have to sum it up as the straightforward equation, that is the expectation, the conditional mean that x given y is equals to this should be your equals to x probability x given y is equals to 1 multiplied by this probability and 2 multiplied by their another probability, and like this all the outcome we should multiply, and we should get what is the mean of that x given y is equals to 2 here. So, that is 1.926. Now, we will take another problem. This is a joint distribution, and this joint distribution is basically a uniform distribution that we have taken here, that is that x and y. So, in many cases we can come across to this one, that they are related through their joint distribution is one some joint distribution, but that distribution, that joint distribution can also be uniform. The uniform density for a single random variable we have discussed, and that there we have seen that for the any value of that random variable, that probability density is constant, probability density is same for the entire range of the random variable. So, similarly, if we just extend this one to that multiple random variable, then it looks like this. So, this is for the, suppose that this is your a and this is your b, and this is your that distribution of this f x of x, if this is your x. So, basically this so this is one, that is 1 by b minus a. Now, if we take it to the 2-dimensional case, so there we will get that, suppose that this is x and this is y. Basically, what we are taking is that this is that so this is that surface where the height is in respect to this joint distribution x comma y x y. This one is constant for the entire range. Say that this is your, so it is not necessary to start with the origin, this can start from anywhere. Say that for the x range is from, so say for example, the way the figure is drawn, that is 0 to say a, and this is say 0 to say b. So, over this entire rectangle, one side is a, another side is b. So, the surface is uniform. So, this type of one problem is taken, and in many cases we can come across of this type of situation where the distribution is uniform. So, f x y y is equals to 1 by 9 for the range 0 to 3 and 0 to 3 for both x and y. Determine the conditional variance of the y at x equals to x. So, similarly we have to so first of all we have to calculate their marginals, and f x of x equals to if we do this integration, we will get 1 by 3, and so if y given x is equals to again 1 by 3 for the conditional distribution, and the conditional mean y given x is equals to 0 to 3, and this if we follow this integration, then we will come that conditional mean of y given x is equals to 3 by 2. Therefore, the variance, the conditional variance, when we are talking about, this should be equals to variance of y given x equals to x is equals to from the minus infinity to plus infinity. This is basically 0 to 3, y minus conditional mean square their conditional distribution with respect to the dy if we do the integration. So, we just fit it in this equation, y minus 3 by 2 square multiplied by 1 by 3, and if we do this integration, we will get the variance is equals to 3 by 4. So, today's class we have covered up to that conditional mean and conditional variance, and we have seen some example problems also on this. And in the next class, one thing is pending for this multiple random variable, which is the moment generating function, and this we will discuss in the next class. Thank you.